Case Western Reserve University's Institute for the Science of Origins proudly presents the Origin Science Scholars Program. The Institute advances the scientific understanding and application of origins and evolution of human and natural systems. The Origin Science Scholars Lectures are presented with the assistance of Case Western Reserve University's Siegel Lifelong Learning Program, College of Arts and Sciences, and Media Vision. Tonight's speaker really needs no further introduction. Because you've got me. But I do want to add that I'm a professor of, well, I guess distinguished university professor of physics and astronomy at Case Western Reserve University. And I'm delighted tonight to be able to tell you about neutrinos. So the first thing to know is that neutrinos are everywhere. They come out of every nuclear reactor there is. Whether it's the sun or other stars or power reactors or natural radioactivity or the early universe. And unlike dark matter, which is hypothetical, we haven't actually discovered it yet, we really know that neutrinos are everywhere. So for example, neutrinos from the early universe, there's about 60 of them in every cubic centimeter of space out there in the universe, and they're concentrated in the galaxy, so there's probably about 1,000 per cubic centimeter in this room. And since they're moving at very nearly the speed of light, that means many trillions of them are passing through you every second. There are also neutrinos coming out of the sun. There are about 3 of them in every cubic centimeter in this room, which is far fewer, but we've detected these ones. We haven't actually detected the ones from the early universe directly yet. And that's because those neutrinos have about 10 million times more energy per neutrino. Okay? In fact, they carry about 3% of the energy of the sun. And interestingly, unlike the photons, the light, which takes about 1 million years to diffuse from the center of the sun where the energy is generated in a huge fusion reactor. Unlike the photons, which take 1 million years to get out and then about 500 seconds to get from the surface of the sun to here, the neutrinos come straight through the sun from the core of the sun directly to us in about 500 seconds. Finally, let me start by noting a local connection. This fellow is Fred Reines, who is the chair of the Case Institute of Technology Physics Department from 1959 to 1966, and won the Nobel Prize in 1995 for the detection of the neutrino in 1956. So it took an awfully long time for them to give it to him, and we'll hear a little bit more about that. All right, so what am I going to talk about? Neutrinos. First, what are they and why do we need them? Second, what do we know about them and how? And finally, a little bit about what's left to learn. And in many ways, neutrinos are so interesting because they're particles that we know exist. We've measured them, but there are so many things about them that we really don't know. So let's start with energy. We all know the word, but what is it? We know it when we see it. It comes in many forms. So we would, if we look at it at night and there's a thunderstorm and we see the lightning coming crashing down, we know that there's energy in the lightning. Okay. If we drive down the road and see a wind farm with solar energy being converted to wind, being converted into the motion of those windmills being converted into electricity to power our lives, we know that that's energy. And we can see then that energy is something that can be put to use. It is something that can do work. And I mean that both in the colloquial sense and in a very technical sense, is that energy is something that can do work. This is another form of wind energy, a less useful form, a much more destructive form. And here's an even more destructive form of energy, the greatest concentration of energy that we've been able to harness, which is nuclear fusion. Okay. Here's a more benign source, one of the ones that we first harnessed on really massive scale, that made this part of the country, in fact, especially upstate New York, maybe a real center for industry about 100 years ago. And one that we harnessed a long, long time ago to really change our species and how it operates. So energy comes in many, many forms. And I'm not going to try to tell you exactly what it is, but there's one very important aspect of energy that we need to know about, which is that energy is conserved. What that means is we can change energy from one form to another, but it doesn't disappear. Okay? It only gets changed from one form to another. And as far as we know, that is exactly true, except in the context of general relativity, where that idea of energy conservation gets generalized a bit to something called the conservation of stress energy. But we're not going to study gravity here very much, or at all, and so we're not going to worry about that subtle difference. And for us, energy is conserved. And that means that if energy goes missing, that it must be a clue. Okay? A clue to one of two things, which is either we didn't understand the experiment we just did, the observation we just made that suggested that energy was missing, or there is an important piece of new physics that is there to be discovered. Okay? And so that's the thing we have to keep in mind for the first part of this talk, that we're really focused on the consequences of the conservation of energy. And one place to pick up this story is in 1896 with this fellow, Henri Becquerel, who in 1896 discovered natural radioactivity in uranium salts. Okay? And he noticed that when he left some uranium salts around, they tended to make imprints on some photographic film that he had. Okay? And this was completely surprising, and so he discovered uranium was radioactive. This was followed up pretty quickly by these folks, Pierre and Marie Curie, who discovered that thorium and polonium and radium were also there and were also radioactive. And the three of them share the 1903 Nobel Prize, making Marie Curie the first of only 2 women physics Nobelists, the first of only 16 women science Nobelists, and the first of only 4 double Nobelists. She won it twice, and the only member of a mother-daughter Nobel pair. Things progressed pretty quickly. In 1899, Rutherford, and I forget which Nobel Prize he won, but he won one, discovered that there were actually 2 different types of radiation at that point. The third one appeared later. He called them alpha and beta, and they were different. One of them, alpha, didn't changed nuclei from one type to another with and changed their mass. So you went from a heavier nucleus to a slightly lighter nucleus. And the other one, called beta, didn't. And Becquerel got into this and looked at this and noticed that, in fact, that beta radiation was just electrons. So it was electrons coming out of big nuclei. Now, remember what I said about energy, that energy should be conserved in radioactive decays. It should be conserved always, and specifically in radioactive decay. So if we see a big nucleus like this is radium 226. It probably isn't, but it'll serve us fine. And it decays by emitting an alpha particle and becomes radon 222. Okay? And when that happens, the alpha particle always comes out with the same amount of energy. Okay? And the amount of energy is equal to the difference in mass between the radium and the radon times c squared. That's that whole E equals mc squared thing. So the energy of the alpha particle comes from the mass difference between the radium and the radon. Okay. Remember, this is not long after 1905, which was Einstein's miraculous year. Right? The year that he told us E equals mc squared, as well as several other things that probably should have won him half a dozen Nobel Prizes. Okay. Well, here is iodine 131, and it too decays, but instead of decaying by emitting an alpha particle, it emits a beta particle, which comes off much more quickly. And remember, it's just an electron. And so that process, iodine becomes xenon 131. They have approximately the same mass. There's a small mass difference between them. The xenon is somewhat less massive than the iodine, and so the energy of the beta particle, the electron that comes off, should be equal to the difference in those masses times the speed of light squared, according to Einstein's formula, except that it wasn't. So energy should be conserved in radioactive decays, But it seemed that some of it went missing, which was a very big mystery. And so that really gives us two possibilities. One is that our law of conservation of energy is wrong. And that was that was really problematic. People really didn't want to give that up. And so in 1930, this fellow, Wolfgang Pauli, made a very bold prediction. People were astounded that someone would go and say this. He said there must be a new particle there. And he called it the neutron. Okay? So he would go on to win the Nobel Prize in 1945 for his many contributions to quantum mechanics. But this was one of the important things that he did, was suggest that what was happening is we were missing a new particle, the neutron. And so what was happening, he said, was that actually two things were coming out of that iodine nucleus. One of them was the beta particle, and the other one was the neutron, and it was the sum of their energies that had to add up to the mass difference squared. Now, in 1936, James Chadwick, who worked with Rutherford, discovered the neutron. So he discovered a neutral particle. That's where the neutron was, because if we would have noticed the particle, the neutron, if it had been charged, we could see charged particles very easily. It's much harder to see neutral particles. So he discovered the neutron, except that it wasn't the right particle. It was much, much too massive to be the particle that Pauli had suggested. He won the Nobel Prize for discovering it because it was very important. It was what allowed us to understand how there could be different isotopes of the same element, how you could have carbon 13 and 14, how you could have different elements with the same chemistry, the same number of electrons, but different masses. That's because they could have different number of neutrons. So it really it was the thing that really catalyzed the field of nuclear physics. But it wasn't the particle that was coming out of iodine when it decayed into xenon along with the electron. Okay. This fellow was Enrico Fermi, who was an Italian refugee from the Nazis and would go on to build the world's first nuclear reactor, the Chicago Pile, and win the 1938 Nobel Prize for his work on radioactivity and heavy elements. And he had a very bold suggestion, which was to change the name of the neutron to neutrino. Okay, which means little neutron in Italian. Okay. So he said, well, there must be a different particle. Pauli wasn't necessarily wrong. It's just that there's more than one neutral particle. We found the neutron. It's very exciting. It goes into making up the nucleus along with protons. But we also have neutrinos, and we should discover those. And he, in fact, went on to write down a whole detailed theory of weak interactions, which are the detailed description of how these particles called neutrinos interact with electrons and protons and neutrons. Now here comes our local connection. Not this fellow, Clyde Cowan. Cowan was an army captain during World War II. And after the war, he went back to school under the GI Bill. And by 1951, he was on the staff at Los Alamos National Laboratory. Later, he was a professor at Catholic University. And unfortunately died in 1974. And we'll understand why, unfortunately, soon. And he got together with this fellow, Fred Reines, who had gone to Los Alamos to work on the Manhattan Project in 1944 with Richard Fineman, went on to be the director of Operation Greenhouse Nuclear Test at Inuiatuk, which was the prelude to Ivy Mike, which was the first thermonuclear device, designed, by the way, by Richard Garwin, a Case alum. And the two of them got together, and they decided to do an experiment at this place, which is the Savannah River site, which had originally been built to separate radioisotopes for the Manhattan Project. Here's a view of that from the International Space Station, and you can see there are a number of reactors there, big nuclear reactors. So they were able to go to one of the reactors, not actually this one, but they all look pretty much the same. This is the L reactor. They worked at the P reactor. And what they did is they put a big tank, a 100-gallon tank of water with cadmium chloride inside of it. And they could get that just 11 meters, maybe from here to the back of the room, away from the reactor. So quite close to the reactor, and about 12 meters underground, so it was shielded from cosmic rays, particles coming from outer space. And why did they do that? Well, they knew that the reactor was supposed to produce the antiparticles of neutrinos, called nu bars. That's that funny V with a bar over it. And those should hit protons in the water and turn the protons into neutrons, according to Fermi's theory of weak interactions, and the neutrino, antineutrino, should change into an anti-electron, called a positron. So they were looking for this process of antineutrinos converting protons into neutrons and positrons. Okay? And the thing is, though, that positron would immediately find an electron in the water. And when a positron and electron, when matter and antimatter come together, they form photons. They form pure energy in the form of very high energy photons, 500,000 electron volts, so a lot of energy. And they would be able to see those photons. And very shortly after, the neutron would hit some of the cadmium and make more massive cadmium and a photon. So they would get actually 3 photons out, 2 right away and 1 a few milliseconds later. Okay? And they would be able to look for those in this tank of water, okay, which is lined with what are called phototubes, which detect high energy photons. Here's a picture of them at the controls of actually a preliminary version of their detector. And here is the sign saying how they won the 1995 Nobel Prize for doing this at the Savannah River site at the P reactor. Now, unfortunately, they won the 1995 Nobel Prize, and the Nobel Prize cannot be awarded posthumously, and so it was given to Rhinus, but not to Cowan. So that's a good point for me to stop and ask questions.
What I was wondering, since you were talking about neutrinos from the early part of the universe, where do are those just losing energy? You said they were much less energetic than the ones from the sun. So so where is that energy going that they're losing?
So we know, for example, that as particles travel through space, through the universe is expanding. So the universe is expanding very slowly, but over a long period of time, over the course of 10 billion years, it doubles in size. It used to double in size much more quickly than that. So when those neutrinos were emitted, they had energies comparable to the center of the sun. Okay, so actually comparable to the surface of the sun. So they were actually reasonably energetic. They were about as energetic as the photons coming out of this light. Okay? And nowadays, they're about 1,000 times less energetic than that. Okay? And the reason is that as they travel through space, space is expanding, and that expansion of space drains energy out of them. So remember I said that energy is conserved except in general relativity? Okay. Well, general relativity is the theory that governs the expansion of space. And so in cosmology, in the study of the universe, where we're using general relativity, we understand that as the universe expands, it extracts energy from particles. Okay. So we know this, we've seen this. When we look at very distant galaxies, we see that the light from them is redder. We call that redshift. When we look at the light from the very early universe, we see that it's actually, even though it was emitted when the universe had a temperature of several thousand degrees, about 3,000 degrees, now it looks like the universe is only 3 degrees. Okay, so it's about 1,000 times colder.
How did you get to be able to make the neutrinos? Like, how did they be able to get to the neutrinos?
So they put their detector right next to a nuclear reactor. Okay? And in just about every nuclear reaction in which there's these electrons coming out, okay, you also get neutrinos. Okay? So every time an electron comes out of a nucleus, pretty much you also get a neutrino or an antineutrino. So they knew that nuclear reactor, they understood the physics of that nuclear reaction. Okay? And so they understood that those nuclear reactors had to be emitting neutrinos. And so that's why they said, OK, we know that there should be neutrinos coming out of that. Let's put our detector as close as we can to that reactor. And the closest they could and do it safely was about 30, 40 feet away. Okay? So from here to the back of the room, not even quite that far. And that's why that was a really good place to measure them, and that's why they did it right next to a nuclear reactor.
If neutrinos are very small mass, very high velocity approaching the speed of light, what makes the difference between a more energetic neutrino and one that's less energetic? Is it mass or velocity or something?
So that's a great question. So for example, photons, which are the particles of light, they have, as far as we can tell, no mass. You know, we've looked for a mass of a photon, and we've yet to discover any mass. And yet we know that there can be very low energy photons and very high energy photons. So if you're in red light, that's relatively low energy. You can get even lower energy by listening to the radio. Radio waves are made up of photons with very low energy. Or you can go to your doctor and get an X-ray, and then you're being bombarded by very high energy photons. Okay? So in the case of, and it's not because they're moving faster, right? So in that case, what's happening is, so particles can have more or less energy whether or not they have mass or not. Okay? Now, in the case of a neutrino, it's a little bit different. We think, actually, and I'll talk about this later, we think that neutrinos, so for a long time we thought neutrinos had no mass whatsoever. In fact, that was probably true until about sometime in the mid-1980s. We thought neutrinos had no mass. As I'll talk about a little bit later, we now believe that neutrinos do have mass. And so that would say that a neutrino that has more energy is moving slightly closer to the speed of light. So it would say that neutrinos aren't actually traveling at the speed of light, only very nearly at the speed of light. And the more energy a neutrino has, the closer it is to exactly the speed of light. Thank you for joining us. You have been watching me, Dr. Glenn Starkman, discussing the prediction and discovery of the neutrino, nature's least interactive particle. For more information on the Origins Science Scholars Program, please visit the Institute's website at origins.case.edu. In the next part of the talk, I will discuss the 3 different types of neutrinos and how they were each discovered. Now, back to the talk. So we now know that there are neutrinos. We know that we need them in order to, so that energy can be conserved. So we're really happy now because that was a very important principle. We didn't want to give it up. We went out on a limb, or at least Pauli went out on a limb and said there must be neutral particles that we don't see, and those are the neutrinos, and that will allow us to conserve energy. And so now the question is, what do we know about these neutrinos and how? And to put that in context, I'll give you a very small refresher course on the Standard Model. Okay. So if we had been talking in 1900, then this is what I might have called the Standard Model. This was the list of all the fundamental particles. There's actually some on there that we wouldn't have known about in 1900. But these were the basic building blocks of matter, the elements, the chemical elements. That was pretty messy. And so we're kind of lucky that we have a much smaller list. It fits on a much prettier slide. And it only has a few particles. It has this group that are here in kind of this reddish, pinkish color called quarks. And there are 6 different types of quarks: the up and the down, the charm and the strange, and the top and the bottom. And the up and the down quarks are the building blocks of protons and neutrons. So a proton is made of 2 up quarks and a down quark, and a neutron is an up quark and 2 down quarks. The charm quark and the strange quark and the top quark and the bottom quark, well, the charm is just like the up quark, only more massive. The top is just like the charm and the up quark, only more massive. Same for the strange, is like the down, and the bottom is like the strange. And they're all unstable, and so we don't see them around us normally. They were there in the early universe when the universe was very young. We make them in accelerators, but they're not there in the everyday world. So, but they're just like the up and the down quark. And then we have the electron. We know about electrons. They go into making atoms along with protons and neutrons. Muons are just like electrons, except a couple of hundred times more massive, a few hundred times more massive. And the tau particle is just like the up and the electron, only more massive still. So we kind of have these 3 copies of things. We call them 3 generations: the quarks, and which go into making protons and neutrons, and these things called leptons, which means light particles, because electrons are about 2,000 times less massive than protons. Okay. And so we have those particles, and then we have this neutrino sitting there we'll come back to, and you see it kind of looks lonely. I put it next to the electron because remember I told you that Fermi's weak interactions described how neutrinos interacted with electrons and protons, and we saw that the electron that came out of the iodine had to be balanced by a neutrino, so we'll call it an electron neutrino. They're kind of friends. Then we have these other particles in purple. They're the particles that mediate the forces of nature. So the one that's a Greek letter gamma, that's our symbol for the photon. It's what's coming out of the lights. It's also what's responsible for electricity and magnetism. The ones to the left of it, the Z and the W, those turn out to mediate Fermi's weak interactions. Those are responsible, those are exchanged between particles to cause this weak force. And the force is weak because the Z and the W are very heavy, and so it's very hard for them to travel very far in some sense. And finally, there's this G, which doesn't stand for gravity, it stands for glue, or gluons. These are the particles that bind together the up and the down quarks inside of protons and neutrons. So we can think of the up and the down quarks sitting there inside the proton or neutron, exchanging these gluons, and those bind them together into protons and neutrons. And finally, at the center, we see this particle that was discovered just 5 years ago, just under 5 years ago, the Higgs boson, discovered at CERN. And it has a very special role that we will touch on a little bit later. Okay. And finally, you see this neutrino, this electron neutrino, and it's sitting there alone, and it kind of looks out of place. Because we have these three families of what are called matter particles, or fermions, named after Enrico Fermi. But only the electron seems to have a neutrino associated with it. And people realize that that probably wasn't how it really was. That the theory, when you tried to write it down mathematically, didn't work so well with just one neutrino. And so people said there must be another neutrino. At the time, we didn't really know about the third generation, only about the first two. And so we thought there had to be a neutrino that went with the muon. And it was called the Neutrino, which is a really awkward name, so people call it the muon neutrino. And it was these three fellows, Leon Lederman, Melvin Schwartz, and Jack Steinberger, who in 1962 decided to do an experiment here on Long Island at the Brookhaven National Laboratory, which had just in 1960 built which has accumulated 7 Nobel Prizes over the years for our investment in it. Pretty good record. And in 1960, it had built the world's premier accelerator, which could boost protons up to an energy that was about 33 times E equals mc squared. Okay, so take their energy, that is the energy of, take the mass of the proton times c squared, that's a certain amount of energy, and it could give them so much, move them so close to the speed of light that they had about 33 times that, actually a little bit more. Okay? And here is, again, is a picture of the Brookhaven National Lab, and you see that very large circle there. And that's not the alternating gradient synchrotron. That's the relativistic heavy ion collider, a much newer machine. That little circle is the AGS, which was for a long time the most powerful accelerator in the world. And they used it to smash protons into beryllium. Now, there's a complicated story. The beryllium then produces these things called pions, which are combinations of a quark and an antiquark, and that decays and produces a muon. And that decays and produces some new electrons and 2 types of neutrinos. This was the important thing. This was a way to get these things called muon neutrinos. So you see now we have an electron neutrino, nu e, and this other thing, a nu mu. Okay? That's what the theory said, that we should be making nu mu's. Now the nice thing about neutrinos is they only interact, they're neutral, so they don't have electromagnetic interactions. They're not quarks. Only quarks have strong interactions. Okay? So there are 3 forces of nature other than gravity: electromagnetism, the strong interaction, and the weak interaction. And the electromagnetic interaction, the strong interaction, are kind of strong. And so if a particle has them, it'll stop in material. Okay? But the weak interaction is incredibly weak. That's what allows neutrinos to come from the center of the sun straight to us. And so that muon neutrino, once you made it, or that electron neutrino, would go through, say, a big concrete block or blocks of lead or iron. And so they could send these neutrinos, the products of this reaction, through some concrete or some lead, a big shield. And then they could be to put a detector on the other side of the concrete to look for neutrinos. And if they hit something on the other side in their detector, what they call the target, the theory said that the muon neutrino should produce muons, and they could then look for those muons. Okay? So it's kind of this strange experiment where you produce muons, and then the muons decay to make muon neutrinos. You send the muon neutrinos through a wall, and on the other side of the wall, you let the muon neutrinos hit things and turn back into muons, and you look for the muons. And even though they were making billions and billions of muon neutrinos, almost all the muon neutrinos went right through the target, just like they went right through the shield. Okay? And in the end, they were able to find 50 events with muon neutrinos. And they could claim that they had detected the muon neutrino, and in fact won the 1988 Nobel Prize for it. And so now we had a much better picture, which looked like this, with with 2 quarks and 2 leptons for the first family, and for the second family, because we had found the muon neutrino. But as we went along and discovered the particles in that third family, first the bottom, and then the tau, and then the top, and then the tau, it seemed like we were going to need one more neutrino. So there's a missing one down there below the tau, to the right of the muon neutrino, and it's called the tau neutrino. Okay. So the person who set out to discover the tau neutrino, he went looking for it, was this fellow, Marty Pearl. He had already won his Nobel Prize for discovering the tau, so he figured he should go and finish the job and discover the tau neutrino. And so he built an experiment called DONUT, or for direct observation of new tau. Okay, so people are starting to get clever. In fact, in the United States, the top and bottom quark weren't called top and bottom, they were called truth and beauty, which led to some interesting other mnemonics, which I can tell you about later. Okay. So they built this thing, and now instead of doing it at Brookhaven, they're doing it at Fermilab, which is just west of Chicago, using a new machine called the Tevatron, which was the new biggest particle accelerator in the world. And it could get protons and antiprotons up to about almost 1,000 times equals mc squared, 1 trillion electron volts, okay, and smash them into each other. And until 2010, until the Large Hadron Collider at CERN turned on, it was the most powerful accelerator in the world. So what did they do with that? They would take the protons from the Tevatron, this beam of high-energy protons on the top left, and they would smash it into a tungsten block, and tau neutrinos would come out of the tungsten block, along with lots and lots of other things. Okay? And then those tau neutrinos, tau particles, very heavy electrons called taus. And those taus would then decay and produce tau neutrinos. It's just like the muon experiment, except with much more energy, because taus have a much higher mass, so you need much more higher energy to produce them. So they would send those tau neutrinos, this beam of junk that was coming out of this tungsten block through a magnet. And by putting a magnetic field on, it would take all the particles that had charge and would bend them out of the path. So only the neutral particles would keep going, like the neutrons and the neutrinos. Well, you had to get rid of the neutrons somehow, so you'd put a big block of shielding, concrete or lead, and you would put that in the way, and the neutrons would stop in that, and out of the other side would come a beam of neutrinos. And that's how we make neutrino beams. Okay? And you would send that to the donut detector, which would basically undo the process. You would send the neutrino beam. For some reason, they made this diagram the opposite way. Neutrino beam coming in from the bottom, and it would go into a target, and it would make taus, and the taus would decay, and they would be able to look for those taus. Okay? So they started taking data in the summer of 1997. They took data for a couple of years, and in the year 2000, they published the result, and they had detected 4 tau neutrinos, and they still haven't won the Nobel Prize for it. Okay. So now we have these 3 solid families. Okay? And that is it for the standard model. We had to wait until 2012 to discover the Higgs boson. So we now have what we think is the complete set of particles of the standard model. 3 generations, each containing 2 quarks, a charged lepton, and a neutral lepton that we call the neutrino. So we have a nu e, a nu mu, and a nu tau. 4 force carriers, the Z, the W, the photon, and the gluon, and the Higgs boson. And that's a good time for me to take questions.
Are the neutrinos then the WIMPs?
What are WIMPs? WIMPs are called weakly interacting massive particles, and they're things that we think might be the dark matter. Okay? Now, for a while we wondered, could neutrinos be the WIMPs? Could they be the dark matter? After all, they have the properties that we think we want dark matter to have. What do we want from dark matter? We want for dark matter to be dark. And dark means that it's hard to see. And the best way to be hard to see is if you don't have electromagnetic or strong interactions. So neutrinos don't. They only interact through what's called the weak force. Okay? And that makes them weakly interacting. So they would be great dark matter. But the thing about, and we know they exist, which is a real plus. Okay? So would they be good dark matter? They would if they were massive. Okay? But it turns out that neutrinos, we now know, are not massive. And we've known that they're not massive enough to be dark matter for about 30 years. Okay? So initially, we thought maybe the neutrinos are the dark matter. But no, they're not the dark matter. So if dark matter is composed of weakly interacting massive particles, then there's some other particle that isn't in this picture. Okay? So there's lots of possibilities for the dark matter, but does not consist of one of the particles on this picture, nor does it consist of simple simple particles built out of this, like protons or neutrons.
This is probably intuitively obvious to everyone else in the room, but I'm just an engineer, so I have to ask. When you're talking about this 33 times and 1,000 times the energy or the mass, are you talking about the Lorentz transformation, m equals m sub 0 to the square root of 1 minus v squared over c squared?
So if I take a particle, say a baseball, and sit it here, it is a certain amount of energy. And that amount of energy is E equal, the AE, is the mass of the baseball times c squared. If I throw it to you, right, then I've given it more energy than that. Okay. And it's not an increase of mass, it's what's called kinetic energy. Okay? So things have energy due to the fact that they exist, that they have mass. That's equals mc squared. And they can have more energy if I throw them, if I make them move. Okay? So that's called kinetic energy. And so what we do at accelerators is we give particles more energy than just the energy associated with their mass. People used to use the language that you increased the mass as you made them move faster. That's a language that tends to lead to misunderstandings. You're not really increasing the mass. You're just giving them extra energy that's additional to their mass. Because they have kinetic energy, they have energy due to their motion. We hope you've been enjoying the Origin Science Scholars Program with me, Dr. Glenn Starkman. In addition to directing the Institute for the Science of Origins, I lead Case Western Reserve University's Center for Education and Research in Cosmology and Astrophysics, CERCA. In the second part of our talk, we learned about the electron, mu, and tau neutrinos. In our final segment, I will talk about how one type of neutrino can change into another on the fly, and what that tells us we have yet to discover about neutrinos. Now, back to our talk. So we know there are neutrinos. We know there are 3 types of neutrinos. We know they were found, first one's near a nuclear reactor, the electron neutrino. And the others had to be made, we had to make the associated electron-like particle, the muon or the tau, at an accelerator, and then let those decay and detect the mu neutrino and the tau neutrino. But by the early part of this millennium, we had discovered all of the particles of the Standard Model, including the 3 neutrinos. And since then, we have been vainly searching for new particles. So there have been no new particles other than the Higgs boson, which is part of the Standard Model, discovered at the Large Hadron Collider. And so people are very interested in what's called beyond the Standard Model physics. Is there physics beyond what I've told you about the Standard Model? And so far, the place to look for that is neutrinos. Because even though I've told you some things about neutrinos, there's a lot we don't know about neutrinos. And I'm just going to give you a flavor for some of that. And you're going to get to learn a lot more about that, I think, from a fellow named Ben Monreal, who is a faculty member here at Case Western Reserve University, who is really the leading young person figuring out how to measure the mass of the neutrino. So let me start with the sun, which is a giant fusion reactor, a giant nuclear reactor fusing hydrogen together to make helium. And fortunately for us, it is a terribly inefficient one. I say fortunately for us because if it was an efficient one, it would be like a hydrogen bomb, right? It would go off in a very short amount of time, and then it would be done, and we'd be in trouble. Right? we'd get no. So fortunately, the sun is very cold in the inside. It's only about 10 million degrees in the inside. A nuclear bomb is, tens or 100 million degrees. So that's why it's so much more efficient. The sun is very cold on the inside, only 10 million degrees, so it's quite inefficient. But nevertheless, that's really good because it's allowed it to be around for several billion years, and it'll be around for several billion more years, very inefficiently fusing its hydrogen into helium, creating photons, and also creating neutrinos. So the sun is a giant source of neutrinos. Now we knew that because we knew the sun was a nuclear reactor, but the question is, how many neutrinos, and what, what energies do those neutrinos have? And the fellow who figured that out was this guy, John Bacall, who in 1963 wrote down what was called the standard solar model. So he took what was known about the sun, and he went through in great detail, making sure that we knew everything that we could, figuring out what was measured, what wasn't measured, what needed to be measured, and he was able to predict how many neutrinos would be coming from the sun and all their energies. And he figured out that every square centimeter, so if we have a little patch like this big, it would have about 10 billion neutrinos going through it every second. So we should be able to look for them. Well, remember, neutrinos are very weakly interacting. So how hard can it be to look for all those neutrinos? And the answer is, you need about 1,000 tons of detector to get one interaction of that neutrino per day, which sounds absolutely crazy. Who would do that? And the answer is this guy. His name's Ray Davis, and in 1969, he took a 100,000-gallon tank of cleaning fluid, perchloroethylene, into the Home State Gold Mine in South Dakota, about a mile underground. And why a mile underground? Because nothing else can get down there. You can get some radioactivity out of the rocks, but no cosmic rays from outer space can get there. It's a very quiet environment radioactively. Okay? And so what he realized is that if one of the electron neutrinos coming out of the sun hit a chlorine in his tank, in this perchloroethylene, the chloro is for chlorine, it would turn into an argon nucleus instead. And that argon nucleus would sit there, not bound anymore, because argon is a Nobel gas. It's very inert. It doesn't have it doesn't bind chemically to things. And what his plan was to count the argon atoms one by one. And he would do that he would bubble helium through the cleaning fluid about once a month to extract the argon atoms. And he was convinced that he could do this with 100%, well, very, very high efficiency. So he could figure out what fraction of the argon atoms he could extract very precisely, and that he could get essentially all of them. And so he would be able to count how many times an electron neutrino had hit a chlorine. He knew what the rate should be, how easy that was to happen. So he would be able to figure out how many of those neutrinos were actually coming from the sun and hitting his detector. And the answer was about 1/3 as many neutrinos as Bacall had predicted. And that was called the solar neutrino problem. So you can imagine there's a few things that we might wonder about when some fellow tells us that the sun has produced all these neutrinos and we have 1/3 as many. Well, actually, we would really worry if he had detected the main source of neutrinos. So I told you that every time, I didn't tell you, but every time we take protons and fuse them to helium, we get neutrinos. Those are called PP neutrinos. They come from the main nuclear reaction in the sun. We don't see those in his detector. They have much too little energy. We see these neutrinos that come from various side chains, reactions that happen only very rarely. So you had to trust Bacall's calculations really at the very, very precise level. You had to guess that not only had he calculated the main nuclear reactions, but all these side nuclear reactions, and that he had really understood the sun, because if you change the sun's temperature by a factor of 2 in the center, well, that sounds like a lot. If you changed it by 10%, then the number of those reactions would change by factors of 2 or 3. So you had to know the temperature in the center of the sun to better than 10%. And that takes a lot of doing. And then you had to really believe that Ray Davis had really extracted all the argon atoms. Had he done that right? Maybe his pumps weren't any good. In fact, he had a problem initially with his pumps, and that didn't help. So this solar neutrino problem, we didn't know which is wrong, the sun or the neutrinos. So is our physics of neutrinos wrong, or is our physics of the sun wrong? Okay. And then there was another problem. You see, we also get neutrinos coming down from the sky, actually also up from the ground because of this. When particles, when cosmic rays, which are particles produced somewhere in the universe that can have extremely high energy, some of them, many, many times what we can get from an accelerator, through the machines that we build. But natural accelerators produce all sorts of very high energy particles that hit our atmosphere. Okay? When they hit our atmosphere, they produce more particles, and those particles hit other particles, produce more particles, et cetera. It's called a cosmic ray shower. And people had worked for a long time to understand how cosmic ray showers develop. And they knew that there would be neutrinos of both electron and muon and tau neutrino type that should be produced in these showers. And one of the things that they were able to predict with great confidence was that for every electron neutrino, there should be 2 muon neutrinos. Okay, because more muons were because of the number of muons that were produced in the upper atmosphere. And instead, when people measured the number of neutrinos, they found that there were about the same number of muon neutrinos and electron neutrinos. And that gave us a second problem called the atmospheric neutrino problem. So now we start to wonder, maybe the solar neutrino wasn't a problem with the sun, because in both cases we're getting the wrong numbers of neutrinos that our particle physics told us should be there. Maybe there's something we don't understand about neutrinos. And it turned out, as far as we can tell, there is something we don't understand. Well, we actually have very good confirmation of this. There's something we didn't understand about neutrinos. Neutrinos have this interesting property, this interesting ability that no other fundamental particle has, which is that they can change type. So I told you there are 3 different types of neutrino, the electron and the muon and the tau. And it turns out that as an electron neutrino travels, it can turn into a muon neutrino or turn into a tau neutrino. And a muon neutrino can turn into a tau neutrino, an electron neutrino, and so on. They can oscillate as they go through space in one into another. It's kind of like, Dr. Jekyll walks out the door and Mr. Hyde shows up. Okay? That somehow they are connected to each other. And so the solar neutrino, the solution to the solar neutrino problem is that inside the sun we have these nuclear reactions that produce mostly electron neutrinos. Okay? We understand those nuclear reactions very well, and we know that they produce electron neutrinos. Not muon neutrinos, not tau neutrinos. But then as those electron neutrinos travel through the sun and then through the space between the sun and the Earth, they become a mixture of electron and muon and tau neutrinos. About an equal mixture, which is why when they get to Ray Davis's experiment, only 1/3 of the electrons, neutrinos, end up being seen, because he can't see the muon and tau neutrinos. They don't turn chlorine into argon. That's really strange. So here it is, you have the sun and some electron neutrino comes out, and by the time it gets out, it's changed into a muon or a tau neutrino. Well, that's really strange. And the reason this happens, actually, well, let's see. I'll tell you in questions. OK, so it travels out through the sun. OK, so that's the first really weird thing about neutrinos, is that they can change from one type to another. Okay? And it has to do with the fact that the way that we think it has to do with the fact that the way the neutrinos interact with the Higgs boson, actually. Probably. We're not sure. Okay? That the way that it interacts with the Higgs boson, basically the Higgs field, which is associated with the Higgs boson, is allowing the electron neutrino to change into a mu neutrino. So if you like, the electron neutrino sees the Higgs field, and the Higgs field changes it into the mu neutrino. Okay? We don't really we understand how this could happen theoretically, but we don't have experimental confirmation of exactly the process through which this happens. Okay, so that's the first really strange thing about neutrinos, about which there's a lot more to learn. Okay, here's the next thing. Right and left. Okay, so it turns out that particles like quarks or electrons and neutrinos should be able to come in what we call both right-handed and left-handed varieties. Okay? Now, that's just a mnemonic. I mean, they don't actually have hands, okay, and they don't choose which hand to use when they write. But this is what we mean. These are particles that have spin. Okay, so you can think of them as little spinning objects. And if they're moving, they could be spinning. It turns out they can spin in one of two ways. They can either be spinning this way. So if they're spinning this way, we call that a right-handed spin. If they're moving that way and spinning that way, we call that a right-handed particle. If they're moving this way and spinning that way, we call that a left-handed particle. And quarks and leptons come in two types. Well, the charged leptons do, and all the quarks, they can either be left-handed or right-handed. But as far as we can tell, electrons only come left-handed. Now, we don't know, well, so right now we are missing the right-handed neutrinos. We haven't seen them. We don't know for sure that they exist. We think they do. Our best guess in the standard model is that those right-handed neutrinos don't even have weak interactions. So they don't have any of the standard interactions that we're able to see other particles, not electromagnetism, not strong interactions, and not even weak interactions. And so we wouldn't see them. And the other speculation is, and this is really speculation, is that they might be much, much more massive than any of the other fundamental particles. So that would be a second reason why we haven't seen them. Okay. But we don't know. We haven't seen right-handed neutrinos, and so we don't know that they exist. We have theoretical reasons to think they exist, but we're not sure. If they do exist, they probably are more weakly interactive and probably much more massive, but not necessarily than the left-handed neutrino. So how massive is the neutrino, and do we know that it has mass? Well, we know that it is less than 1/millionth the mass of an electron. Okay. So we've gone and directly made measurements that look for the mass of a neutrino. And you're going to learn a lot more about this from Ben Monreal, because he is building a new experiment that will improve the direct measurement, attempt to measure the mass of a neutrino, because we haven't actually seen the mass yet. But we do know that at least 2 of the 3 of them aren't 0. And the reason is that massless particles, it turns out, can't oscillate from one into another. If the neutrinos were perfectly massless, they wouldn't be able to oscillate from one into another. And so it turns out that at least 2 of the 3 of them are need to have some mass in order to be able to oscillate, but less than 1/millionth of the mass of the electron. We also know from cosmology, from looking at the microwave background, that the neutrinos aren't more than 1/millionth the mass of the electron. Okay, so we have hopes of seeing the mass of the electron both in our laboratory and through cosmology, but we haven't seen it yet. But we know that they have mass. It's a kind of strange situation where we're convinced that a particle has mass because our theory tells us it has to have mass, but we haven't been able to measure it. And that's the mass of the left-handed neutrino. As to the mass of the right-handed neutrino, we have no idea. Well, we have ideas, but we have no experimental tests. So you can see that this is the one part of the standard model where there are an enormous amount of questions. Okay? And it's a real frontier for doing particle physics. It's also a frontier for cosmology. So we have talked in the past about the cosmic microwave background, which is light that last scattered. The universe used to be very hot when it was young, and as it expanded, it cooled. And when the universe was about 3,000 degrees, when it was about 400,000 years old, the light stopped scattering off other stuff. And it did that because the protons and neutrons and electrons got together to form only neutral particles. So they formed hydrogen atoms and helium atoms. And hydrogen atoms and helium atoms are actually quite bad at scattering light. Neutral particles are very bad at scattering light, and so the light stopped scattering and started traveling straight through the universe ever since then. And it's been traveling for about 13.8 billion years since the universe was 400,000 years old. And it's been stretched with the expanding universe, so now instead of looking like the universe is 3,000 degrees, it looks 1,000 times cooler, about 3 degrees. Well, there should be neutrinos out there, as I told you before. There should be there should be many of them from the early universe. They last scattered when the universe was 1 second old. So they were emitted when the universe was much hotter, when it was about 1 million times hotter, and when it was much younger, when it was instead of 400,000 year olds, just 1 second old. So we would love to see the neutrino background, because that would give us a snapshot of the universe at an age of 1 second. And whereas our best information is much later now, it's when it's only 400,000, already 400,000 years old. Okay? So we would love to see those neutrinos. The ones that I told you were about 60 cubics per cubic centimeter on average, and maybe 1,000 in this room. The problem is that those neutrinos have very little energy. It's incredibly hard to see them, much harder than it is to see neutrinos from supernova from the sun. They have a very tiny amount of energy, and the schemes to detect them are kind of outlandish. There are things like, and so here's the scheme I came up with about 20 years ago. So you take a block that weighs about 1,000 tons, and you cool it to about 1 degree. And then it turns out, if you have a nice block like that, the neutrinos will actually scatter off it very nicely. And you can actually get the neutrinos to push the block. Okay? So if you put a spring on the end of the block will kind of start oscillating against the spring. Okay? Except the neutrinos don't exert very much force on the block. It's about the same pressure, is about the same as the weight of a fly on the city of Cleveland. Okay, so imagine that we took a fly and we spread it out nice and thinly over the entire city of Cleveland, and I said, okay, now can you please take your scale and weigh that? And that's what you're trying to do. So it turns out the block would move about 1/1000th of a centimeter after a year. It would compress the spring. We can imagine doing things like that, but they're kind of tough. Okay? So we're hoping one day to measure this neutrino background. It's one of the holy grails of cosmology, but it's terribly difficult. But if we could, it would one day tell us what the universe was like when it was just 1 second old and 10 billion degrees. So that's all I have to tell you today about neutrinos. They're really remarkable particles. We know they exist. There are all sorts of mysteries about them, and we hope to uncover the answers to those mysteries both by making neutrinos in our accelerators and building detectors to detect them, by measuring them in the laboratory, measuring their mass, and by looking at the universe to see the effects of the very small mass of the neutrino on the universe and on astronomical systems. Thank you. The Origin Science Scholars Lectures are presented by Case Western Reserve University's Institute for the Science of Origins, with the assistance of the Siegel Lifelong Learning Program, the College of Arts and Sciences, and MediaVision. For more information on the Origin Science Scholars Program, including a full video archive, please visit the Institute's website at origins.case.edu.